Okay, talk a bit about the history of this stuff. There's some phases. I just, there's so much stuff and I get lost in detail all the time. And so I talk first about pioneers. And the pioneers mostly have to do with the army. This is Hans Kleinwachter. He was a physicist working for the German army, and he was part of the team which developed the V2 rocket. I found this very recently. I still don't completely understand how this works. I included it because it uses cathode ray tubes, like these kind of tubes you have in television and oscilloscopes, to actually compute, which is really interesting. So it uses them to show the result of an equation. Like you have a very simple electrical circuit with a tube and a coil and some power sources, and then they use a kind of special made tube with a kind of resistance rod in it to do equations. So I thought it interesting that, from the beginning, the goal of this stuff is to actually see mathematics on the screen. I mean, that's what this is all about. This is not about getting a number out. This is seeing curves of equations so that you can interact with them. This is completely obscure. I just found it and nobody else ever wrote about this stuff, so I have no idea. I mean, we still have to find out who this guy really was. And then the pioneer, which is a bit more well known, is Helmut Hölzer, is the guy behind the sort of black box in the V2 rocket, like Derek talked about it yesterday a lot. He had this beautiful picture of the V2 rocket, and there's these boxes which contain what was called the Mischgerät, like the mixer. And this is a kind of diagram of how they did multiplication, which was interesting because there were not really standard multipliers you could just buy at that time at all. And this is what that Mischgerät actually was. So this was in the V2 rocket. And what it did, it got some inputs from an antenna, like they had a kind of radio beacon pointing towards London. Or actually, I don't really know how that works. I guess it's pointing to home, more or less. But anyway, you have some kind of direction, like where you came from. And then there's different axes, like they had gyroscopes. So sort of, there's basically position sensors, you could say, for orientation sensors. And then the thing is, like, the V2 rocket have this kind of curve, and you want to sort of know where you are in the curve. So you have to sort of integrate. You have to, like, the rocket goes like this, and you have to sort of remember, okay, I went that way for so much time, and so it means that I'm now here. And that's operation which I just described in words. That's called integration. So that's what these Mischgeräts actually does. So it's basically doing the equation, and then the idea was, of course, that it would sort of go in this curve and hit London. So this is about war, it's about missiles, it's about projectiles, that's where this stuff comes from. And then later this Hölzer, he thought, okay, if I can do all these mathematical operations in this little box, I can also do it in the lab and use it as a calculator. So he built this machine, which is in a way the first functional analog computer, where you have like modules doing different things, and you can patch an equation and you can use it to simulate. Like this Hölzer guy was also working on the V2 rockets, of course. So after the Second World War, he was sort of kidnapped in what was called Operation Paperclip, where they put like people like Werner von Braun and sort of imported them all to the States and said, well, you have a choice, you can go to jail or you help us build these rockets. And then he became the head of the Jet Propulsion Laboratory. So he was, for a long time was in the sort of aerospace industry. So you could say he's the inventor of the analog computer, even though this machine had no follow-up. This was obscure, like this was hidden. It was classified for a long time, and the American analog computers came from another source. They came from this guy, a guy called George Philbrick. He's also the guy from the Lightning Empiricism, which I sort of stole for the title of this talk. Really funny guy. And in 1938 he developed this machine, which he called Polyphemus, which is like from Greek mythology. It's a monster with one eye, and the one eye is the oscilloscope. So it's sort of up there. You see this curve there. And basically, if you look at these two machines, it's the same machine but with a different front. So basically, it's like a fixed analog computer. It can just only do one equation, and you have these knobs, and you can sort of turn the variables. And this one equation can be, this is something about flux, so I don't really know what it is, but this something with water flow. This, you know, like it can be applied in different contexts. So it can be a model of like water flowing through a factory or something, or it can be a model of electricity flowing somewhere. But the idea was, and that's very important, is also what I do here, is that it's what he called repetitive operation. So it's doing calculation 20 times a second. So you can look at it on the screen and you can turn a knob and then you see the curve change. So it's interactive. So it's not about plotting. It's not about getting a precise value. You can also do it with these machines. You can put them in the slow mode and then you can plot the curve. But this was really for interactive, exploration, which in 1938. Like computers didn't, like digital computers didn't exist. It's you have a machine where you can turn knobs and do mathematics in real time. Okay, well he wrote lots of stuff. Like during the Second World War, he was hired to think about fire control, and that's what Derek talked about a lot yesterday, about the incredible history of all this war technology. And you can safely say that all electronics we know now comes from the Second World War, and it's sort of is a result of United States pouring billions and billions and billions of money into the military research. That's where like our current computers come from. That's where all this electronics comes from. That's where this stuff comes from. To go back to Philbrick. So all this stuff was of course secret, and then in 1946 you have this beautiful series which was published by the RAD lab. It's the radiation lab of MIT, where they basically invented or developed radar further. They have this, it's if you have the whole series, which I don't, it's like you have a whole shelf of books containing all the knowledge about cathode ray tubes, about radar tubes, about op amps, about all this kind of stuff, about analog computing. And Philbrick was writing, he was involved in fire control. So fire control is basically like they were thinking of systems because these planes and rockets are so fast that humans cannot follow them anymore and shoot them out of the air. You need machines to do this. So you need a machine which can analyze a radar signal and sort of point a gun at a moving plane, which goes too fast for humans. So that's basically what this stuff is all about. And then I have to also read this and not look at the screen. And then here it's interesting because he wrote a kind of summary of his war work in '46 in this book, which was also classified, and it was declassified I think somewhere in the '50s. And then he talks about like these computing machines that if you set up, like you make a circuit to compute something and you want to compute something else, you have to make a new circuit. So that's annoying. So I'll just read it, what's here. Frequently during several of the developments above described, it has been thought and said that for the increasingly diversified uses to which the simulative methods were being put, requiring new construction or at least major physical rearrangement of components each time, it would be preferable to build an extremely general and flexible assembly, covering every conceivable type of system, which could be adapted to any particular problem simply by the manipulation of conveniently provided organizational controls. Knowledge of the means for achieving quite impressive generality had gradually been gained, and the proposal for such a super simulator, as it came to be denoted, was considered not at all fantastic. After all, witness the differential analyzer. That's this mechanical machine I talked about. Yeah, and then he basically says, well, if you do something like that, but then electronically, you can have like the super simulator, and then you can simulate everything. And then at the end, the sort of utopian, well, I don't know if it's utopian, but then he talks, for instance here, warfare amongst his missiles could just be staged and observed entirely in the laboratory, possibly with statistical machinery in attendance for interpretation and assessment. Years of experience and of trial and error on the development of controls and dynamic components could thus be collapsed into hours. There is in reality no limit at all. So the idea is that you can then fight like virtual wars in the lab in your analog computer, and then the development goes much further. And then of course you can also think, well, then you don't have to do the real thing anymore. You can just give points to the two parties and that's it. Anyway, so this is a whole history, of course, of, you talked about it a lot yesterday, about sort of virtualization and war games and all this kind of stuff. So that also starts somewhere here. Like he's describing stuff which happened in the middle of the Second World War. And then, yeah, to continue a bit with Philbrick, after the war he started a company, George A. Philbrick Research, and they started making these modules, like beautiful black boxes, which are basically like, it's like the first modular system. So inside they look like this, they were with tubes, the computer tube, this beautiful word, computer. And then, like a typical setup would look something like this. So you have like a lot of these boxes, and then of course you have oscilloscopes, like things to look at, so that you can actually interact with this stuff. And then he had this sort of, what was it called? Intentionally unperiodic magazine of this company. I mean, he was a funny guy, he could write. So he had this beautiful title, Lightning Empiricist. So it's really about the idea that you can, be empirical in mathematics. Like you can, sort of surf the waves of these equations and think, oh, this is a cool spot here. And then this sort of gives overview of, the new stuff they build for various companies. So they have this intentionally unconventional analogery about a sort of special thing they built for an installation in, I mean, it's easier for you to read on the distance than for me. Somewhere, oh yeah, here, Hercules Power Co., somewhere in Utah. I can just go a bit, so this is the display of that big machine you just saw. This is another installation here, a new installation in the physiology department of Western Reserve University Medical School. These are some other ones. Portsmouth Naval Shipyard, Army Electronics Research and Development Lab, Dow Chemical Company, the Process Control Laboratory. So basically what they do here, they have their sort of pools, their control panel for their whole factory. And then this is the simulator of the factory. So this is an analog computer which simulates the factory so that they can test their control panel and educate perhaps also people who have to work there. But you can see they're like enormous machines, and there are plenty of them. I mean, they, like every time they have this new. And what's relevant for here, like if the vector hack, is that always this is, where the truth is. This is where the stuff emerges and where you can actually see what you're doing. It's okay, new gear, it's like sort of a magazine. So this is, well, some of them are still around. This is how they really looked. And then this is the kind of display system they would make. So they had very clever things where they would have equations, but then they would have generators for like lines, it's like markers. You can actually really see where the equations, where the points are, and you can, do like pretty precise stuff. Another pioneer I want to talk about briefly, because it's also very much somebody who's thinking about how to display this stuff. It's from this book. It's a guy called Donald McKay. He was working in England. And he, in the 50s, also 53, he did this beautiful research which turned into this book. And this book is called Analog Computing at Ultra High Speed. And it's actually pretty high speed. I mean, it goes into the megahertz. And it was all done with tubes. And it was not, because he was working with such high speeds, he didn't have cables, he was just soldering stuff directly. So in order to have, avoid the capacitance of cables. And then also there you have this beautiful scope, round scope screen. And he was very much into, I have some quotes, but I'm already looking at the time a bit anxiously, so perhaps I'm not going to read the quotes. But he was very much thinking about how people can engage. He was thinking about, okay, you can compute all this stuff at super high speed, but how can we actually get this information into our system and engage with it? So he thought of all kinds of clever ways to have like variables move automatically. So if you have two variables, like one is sort of changing automatically. So instead of having one curve, you have a whole landscape of curves. So you could really get a sense of this whole equation system you're studying. So you can really look at this stuff all kinds of ways. So he invented lots of stuff like these markers, which you would put at some point in the curve, so you can really see the also the speed of these curves. Well, this kind of stuff. What's also really interesting is that he thought about multi-dimensional display, so like three-dimensional. So all, I mean, of course, if you have a systems with like 3 systems of equations in X, Y, Z, then you already have a 3-dimensional mathematical object. So you were thinking, okay, how can we look at this? So you get this very beautiful equation landscapes. But he was also thinking about doing things stereoscopically. There would be a way to sort of grasp more of this simulation. And then what's also interesting, he said, well, you know, there's no way to stop, no reason to really stop at 3. We can also do 4 or more. And then you get the 4-dimensional tesseract, like a 4-dimensional object, which you can just also rotate in all dimensions, and you can get a feel of what this 4-dimensional object looks like. And 4-dimensional climb bottles, like all these sort of weird mathematical objects. He was really far ahead of his time. But he was like a small, you know, researcher, more or less independent, working in a university, and pretty much in the beginning of the 50s, all universities with a sort of good engineering department or electronics department, they all built something like this. So this is Dutch, it's from the vaults of the Delft University. It's like from the 50s, analog computer they built in Delft, in the technical university there. I'm sure if you go here in Zagreb or in Belgrade or everywhere wherever you may live, you go to the local university, they have also somewhere a vault with these machines, or they have pictures of them. You know, it was everywhere. So you have these small, university labs, researches, and then you have the huge military projects. It's a project called Cyclone. So this is like, at that time, beginning of the 50s, it was the biggest analog computing installation in the world. So it was, I think it was like 300 amplifiers. So you have all these amplifiers, all these knobs, like it's basically a very big version of this thing. And then at the back you have all kind of plotters which plot curves, and then here you have also plotters which plots an XY curves. And then this is really cute. It's like a 3-dimensional model of a rocket. You can actually see it sort of move. Goes like this, so they can, because this was mostly about getting missiles to go to the right place. So it's a bit like a sort of follow-up on the V2 stuff. You have crazy big installations. This is another American one. This is the biggest one I know about. It was called Tridac. It was in the United Kingdom, the Royal Aircraft Establishment. So it's like a whole building with everything in there, like a big computer, power supplies, everything. So it was actually built and operated for quite a few years. So it's this huge installation. And then this is also a big one a bit later. It's from NASA, which was used for the first moon missions. They basically what they did is to program all the equations of how you get a rocket to the moon. So you have to sort of imagine like these guys sort of turning knobs and go like, ah, this is a trajectory, this goes to the moon. And then what they would do is to sort of explore the space of possibilities and think, okay, this trajectory actually goes there. And then they would give it to the digital department, which would use the same values and would confirm. And this is real time. In the digital department, it would take like, I think like 10 hours to compute the same trajectory, but then it was much more precise. And then they knew that, okay, that's where we have to go. So this is NASA. Okay, and then later you have, okay, this is like the first phase. You have like, well, the first phase is pioneers. Second phase you have like university researchers and these big contracts. And the third phase is you get companies. That's how it worked in the States. It's exactly the same how it worked with digital computers. Like the military invented this SAGE system, and then IBM suddenly was in business because they could sell computers and they had clients which bought all these crazy expensive computers. Just the same with analog computers. The military would buy all this stuff, but Boeing would be a company and build this stuff. So this is Boeing. This is, I think, Beckman. Like there's all these big companies. Goodyear. This is a French company, also in the 50s. These are the Russians, which also late in the 50s. They also built like these analog computers. And then the Germans, after 1945, for 10 years they were prohibited to do anything dangerous. It's like they were not allowed to build rockets and these kind of things. And also analog computers, they could start building in 55. So in 56, Telefunken sort of brought out their first analog computer. And this is a later one, a very beautiful machine, like the most precise analog computer I'm aware of. And then this biggest company was a company called EAI, which from the States, which built this model. So this is one installation in Germany for the aerospace laboratory. And this is mine, like the one I have. This ad, like the first desktop. But this machine was, everywhere. I mean, there were thousands of these things were built. Like universities had them. I know at least 3 labs in Holland which had them. Like now they don't have them anymore. So these things were quite current. And now I know there's about 15 left. And mine, there's 2 which work, and mine is one, and mine is the only one which gets used for things. Anyway, I'm going to speed up. So these are the later ones. It gets bigger and bigger. This was a big calculation center they had in Brussels, where you could come with your equations and then people would put it on the machine and then you could go home with your plot. And then, well, there's more of this stuff. And then a sort of later phase, you basically get like small machines like this one built for the American Marines. And then this one, like this is the same actual machine, but before I repaired the display. And these were built for education. So this machine was designed in '68 and production stopped in 2004. So it was built for 36 years, unchanged, without any change. So you have to look at your iPhone, look at your laptop, and go like, crazy. I mean, but it was, because it was used for education, I mean, it's extremely simple machine. There's nothing in there, I showed you. So yeah. So basically, at the sort of latest stage of analog computing, you get these machines are sort of left over for for in schools. So you can imagine like you have a classroom with 20 of these things and students trying to figure out how op-amps work and learning all the basics. And then on the other side of the spectrum, you had this super expensive hybrid computers, which were basically analog computers, which were controlled, where all the patching was controlled by the digital computer, which makes a lot of sense because then you don't have to do all this stuff. All the pods are also controlled by digital computers, because digital computers were slow, extremely slow, and analog computers were very fast. So there was like sort of the best of both worlds. For a very long time, people thought that this is the future of computing. That this is, this makes sense to do these both. And this is the most beautiful machine in history. I think it's a gorgeous machine. It's the AD4, Applied Dynamics 4. It's also a hybrid computer, so you hook it up to like a PDP type big mainframe machine, and it's it's an incredible machine. This is in the Science Museum in Ghent, in Belgium. They have one. And then in Delft, I talked to the guy who ran the analog computation lab, and they only have their patch panel because they had 4 of these machines, and they only have the patch panels because these machines are so big they couldn't keep them. And that also brings us to the demise of these machines. Like if you run code, like digital code, you can pretty much run the same code if it's not assembler, if it's like C, on different computers. Like you have compilers and you can run the same code on different computers. With this, you can sort of keep the patch panels, but you can only put that patch panel on an identical analog computer. So for science, like big science, where you have labs in the whole of Europe collaborating on things, it's actually not so easy to exchange things or test stuff or verify things. So that's part of why this stuff collapsed. And then, so I mean, I already gave a kind of overview through all these slides and where they come from the kind of stuff people did with it. Like a lot of it was aerospace, a lot of it was nuclear power, a lot of it was fire control, missiles, this kind of stuff. And then all this different like biological models, all this kind of stuff. But also an area where they stayed quite long was in things where it was direct interaction. So think like flight simulators, because digital computers until, let's say, 1980, to put it very bluntly, digital computers were too slow to do anything real time. I mean, perhaps, there's always exceptions, but just generalizing. So all this flight simulation stuff, so you get this very beautiful sculptural stuff where you have this like machine and then this sort of crappy stuff, props in front. And also they showed actually, simulations. Yeah, you would see like perspective curves, like you would see like real-time animations. Like yesterday also you showed like first computer animation. If you look really close, you can also see how slow those digital computers were in the 70s. This was real-time and it was pretty smooth. I mean, it's, if you can, just what you saw here, it's just really real-time. So this is well, this goes on like this. Okay, I look at the time. okay, computers now, there's one guy, Bernd Ullmann, who has the Analog Computing Museum. He has like an incredible collection, and he actually builds this stuff. So he sells things, and he actually sells. I mean, he doesn't sell much. I think he sold 2. I haven't asked the price. I mean, they're really not cheap. I think they cost like 20,000 euros or something in that order. Sorry? Oh, it's actually not so expensive. Okay. Yeah. But for instance, he sold one to, he told me, to a biophysical lab where they do a lot of calculations in protein folding, and there's one part of the equation which is actually quite slow on the digital computer. So what they do, they hook up this to the digital computer, and then they, like this part of the equation always goes to the analog machine, and it's much faster than doing it on even on the graphics card apparently, which I found surprising, but you know, good news. There's all kinds of weird research into analog computing. I mean, it's certainly not that. It's what you get now is that people are you're hitting the limits of what you can do with the sort of traditional chips in the digital computers. So people are also looking at like unconventional computing. So they start to look at this analog stuff. Okay, how does this work? And one of the most intriguing ones is this guy called Jonathan Mills. He published until 2004. He's still alive, he's still active, but I suspect he's been gobbled up by the military. He cannot publish. I'm sure he's inventing all kind of weird stuff. And what's interesting about it, that this is a kind of analog computer in there, but part of the calculation happens in this piece of black foam. So it's part of it is like a, you know, I showed you this direct analog stuff where you have this, you know, resistive paper. So part of that stuff is here, like some kind of part of these equations are like, it's basically a piece of black foam with some contacts, and then you put voltages, and then you measure somewhere else, and then you have solved an equation. I mean, it's really, I mean, but just the idea, there's great articles of him when he was still publishing, where he's described as his mad professor, which then sort of goes to the digital department, gets the packing foam of the digital computers, and then turns it into an analog computer, which I find fantastic. And then this is super, like, is the prototype 3D EAC. It's like the extended analog computer. It's a long story, but it's the extended analog computer is like a kind of mythical machine which is faster than a Turing machine, or can do more than a Turing machine. And this is in 3D, so it's basically a pot of jelly with a lot of electrodes, and you know, it computes something. And this is, no, I'm not going to go into there because it's... Okay, to talk about art, I'm not going to talk about this. This is Desmond Henry, who used mechanical. So I'm not going to talk about mechanical analog computing, so don't look. I'm also not going to talk about James Whitney, also the same, you know, mechanical. Here it gets a bit more interesting. This guy is Gordon Pask, crazy cybernetician, and he was working with Solartron, which was one of the English manufacturers of measuring equipment and analog computers. And he was interested in building learning machines. There's a great slide which I don't have, unfortunately, here, but where you see 3 of these boxes, and one is the teacher, and the one is the pupil, and in the middle is a control panel, and they, you know, they have a didactical interaction. And one of the things he developed is this machine called the Music Color, which is basically a learning disco organ. So you have music playing, and then there's a light show, and then you can approve or disapprove, and it learns. And it actually learns, apparently. So it's you know, it's analog, but it's not really an analog computer. So this is sort of stretching the limits a bit. This is another one, the first interactive installation, as far as I know. Nicolas Scheffer, Hungarian French artist. 1956, he built this sculpture which is on wheels, and it reacts to sounds, and it also, there's, you know, analog electronics doing the computations inside. But if you go really, if you're really strict and say, okay, I want to have a general purpose analog computer like this stuff, this is the analog computer in the Hamburg synchrotron, like a particle accelerator. And then there was this guy, I have to look up his name, he's extremely obscure, and I really apologize for the bad quality of the internet picture, the only internet picture I found. And this guy is called Kurt Alsleben. And he was an artist, and through his friend he got into this computer and made this plotter art. I have no idea if he made more. I mean, it's something I have to also investigate more. And then this is an older extremely bad picture by Roland Fernhuber, who worked at Euratom. He was a particle physicist. He worked in Brussels, and he used in his spare time the plotter and the computer to also make art. Well, the most interesting ones of these ones is the people who really use analog computers is Erkki Kurenniemi, the Finnish maverick instrument designer, futurist, philosopher, crazy guy. He used the same computer I have, actually, the TRP, it's up there, light toxin or whatever, and then Pace TR48. That's the one I have. He used it for a project with Jan Bark, which became a film, which was eventually broadcast on Swedish television. And I can show a short fragment of it. And there's some sound. And then there's another guy, there's David Rosenboom, who's a sort of famous American composer who made one piece which is called Music for Analog Computer. We're not going to listen to it, but he used this machine, I mean this type, it's like a very simple tube analog computer to make it. And that's about it. I mean, there's not so much in that time. We can talk about why this was. I think partly because when these machines became obsolete was the time where, I mean, you talked about it also, Derek, yesterday. Like after 73, kind of computer art was out, and that was the time when these machines became obsolete. So I think one factor could be that the moment these machines became obsolete, this kind of art was not very, in demand or like welcome. I don't know. I mean, I'm really surprised because these things were also more rare than digital computers. But well, we can think about this, why this happened. And then later, like more recent, this is a picture of the Analogue Studio in the conservatory in The Hague, where I was studying there. So I spent like 2 years in the studio, during 2 years, one afternoon or one evening in the studio making sounds. And at some point I started like using all the analog equipment and only looked at the oscilloscope, and I didn't really make sound anymore. And then one day these machines emerged, like these two crazy machines with like wires, and going, wow. And then I think, well, you know, if I can understand this, there's no reason I cannot work with this. And then I looked at it and I had no clue what this was all about. I didn't understand what the modules were. And these were analog computers. And later I found out that this was a project of Hans Kulk. This is his home. It was his home. I mean, now he has a studio, but he had this small house in Den Bosch where he lived. He still lives. And it's like a small bedroom. And if you go in, it's like a submarine. Like all the walls are covered in this beautiful 50s generators, like everything tubes until the ceiling. I mean, it's fantastic. But now he has all this gear in the studio, which is a bit better. And in the end of the 80s, beginning of the 90s, when all the technical universities in Holland scrapped their analog computers, he went to all of them and he collected them. And in Holland, they all bought the same, like all the technical universities bought the same. So he has like, well, at some point he had quite a few of these. He gave them away, some things got lost, some things, you know how it goes. There's 2 left, but you know, still. He inspired lots of people, like he inspired like Bernd Ullmann, the guy who still sells these machines, to be interested in this stuff. Yeah, I called him when I discovered that he was the guy who put these machines in the studio. So he's there. There's a guy called Andrew Fitch who lives in Perth, who, like on the video circuits, people on Facebook certainly know him. He's Nonlinear Circuits, and when he started building his own like synthesizer circuits, one of the things he built is like a portable analog computer, just to like for sound generation. And then the stuff he builds later, and he sells also like Eurorack modules, this kind of stuff. Well, this is my studio at the moment. So yeah, the kabelsalat is a word I learned, like a beautiful German word for cable salad, spaghetti. I mean, salad is better. So basically, very briefly, what I do is I restore this one. I have another one which is actually here, but okay. So this is a slow analog computer, and I built a machine like this. Like you can see that these machines are quite slow. I mean, they draw like this, or you can use them to make sound, but you cannot use them really to make video. And what I wanted to do is to basically build, and that's what I did here, I built all these modules which are the same as an analog computer but then made for very high frequencies like megahertz, 10 megahertz, so that you can do HD video signals. And so that you have all these BNC cables. I mean, it's a nightmare. It's not like cable salad, it's like a forest. You sort of have this tool, like a BNC insertion tool, where you go like, because all these cables are stiff. I mean, it's like, you know, nightmare. But you know, it works. And I control this machine with the signals coming from the slow one. So anyway. Okay, so I talked about history. I talked about some, like, the very rare artistic use I could find. Like, if you know, think, oh, you should talk about this, then please come to me, because I'm really eager to hear about these guys, or I mean, mostly are guys, because you know it's so rare, and I also don't really know why. And then it's a very interesting, very direct influence is the influence on the genesis of the modular synthesizer. Like, this whole idea of modularity comes directly from the analog computer. I'm looking at my phone because I'm super bored and I want to look at Instagram because I have my quotes here. So one of these three people, I don't know who, somebody knows, is Bob Moog. Bob Moog, the guy, the inventor of the Moog synthesizer, like the sort of first commercial electronic synthesizer. I mean, it's a rabbit hole. I studied electronic music. I know this is not the first, don't get me wrong. But, you know, the first modular synthesizer, which was sort of, you could buy in the store. And then this is basically what he invented, this thing called voltage control, so that you can, instead of, you know, turning a knob or playing a keyboard, you can also have a signal controlling the pitch of some kind of tone. And then this Bob Moog, he studied with, in Columbia University, he studied with Ragazzini. Ragazzini was the guy who invented the op-amp. So you sort of think, well, this guy must have known about analog computers. But then he wrote, like, the article where this picture is from, he says basically, these circuits, which are shown in block form in figure 3, borrow their design concepts from analog computer technology. And also when you look at this, I mean, if you look at the kind of diagrams you see in analog computing books, I mean, it's really this kind of stuff. Like, this is an adder, this is a kind of exponential thing. So you put a signal in and it comes, an exponential curve comes out. And then this is other stuff which sort of does the sound. But like, the basic of it is really like from analog computer. And also Bob Moog talked about a guy, Austrian guy called Harald Bode. Well, okay, so these are big Moog setup. Harald Bode, that sort of the idea of making a synthesizer modular sort of came from this guy, a guy called Harald Bode. I'm looking again at my quotes. So this is the first machine which Harald Bode sort of built, which is modular here. Like, there was some kind of tape loop system here, but then here you have a kind of modular system of filters and generators. And then he talks in an article also here, the modern approach of synthesizing intricate electronic systems from modules with a limited number of basic functions has proven successful in the computer field. That's also interesting, huh? If you read this paper and you don't know about analog computer, you think, computer field. Okay, so he's talking about code. But no, he's not talking about code, he's talking about analog computers. There's lots of articles, since I'm busy with this obsessive stuff, that you read this article and you go like, of course, yeah, they just plugged it in. It's not a, so that's also something, because it's forgotten, it's, you know, you have these mechanisms that it sort of gets buried even more, because people think, oh, so this Harald Bode used a digital computer, I read that somewhere. Anyway, okay, and this approach has now been made in the area of sound synthesis. So then he talks about it's flexible, versatile, and then it's all about exploration and production of new sound. So it's also the idea behind making something modular is that you can try out things very quickly. You have a kind of lab tool. So it's also very similar in ethics, you could say, as why these analog computers were used in science and engineering. It's to serve the waves of the equations, and here you can serve the waves of the sound. And this also, like, this is from his notebook, Harald Bode, his personal notebook, so it's in German. And then here he talks about the pultform, like the form of this thing, like he's talking about his machine, like he's going to invent this synthesizer and then how it should be built. And then he said, well, yeah, it would be nice to have this pulled form which is already known from the Heath computer. And the Heath computer is, the Heathkit is this one. Oops. Like Heathkit, they built 2 analog computers, and this one is the one with the beautiful pulled form. Okay. I'm just making a case. I mean, it's obvious, I guess, that these analog modular synthesizers come from analog computers, but you know, I'm assembling proof, which, you know, if we are short on time, we can skip this. Like, I guess you believe me, but it's also nice. This is Don Buchla, who built this beautiful modular system. Our idea was to build the black box that would be a palette for composers in their homes. It would be their studio. The idea was to design it so that it was like an analog computer. It was not a musical instrument, but it was modular. It was a collection of modules of voltage-controlled envelope generators, and it had sequences in it right off the bat. It was a collection of modules that you would put together. There were no systems the same until CBS bought it. ARP, well, you know, I can go on. ARP worked for Philbrick for 25 years or something, 20 years, so, you know, he definitely knew about analog computers. So I'm not, this is Nexus, which is a company founded by the same guy as ARP, and they basically built, they sort of copied all the Philbrick stuff. I'm going to go a bit faster, and this is from Dennis Collin, the guy who designed the ARP filter, which is very famous, and he says, well, it's basically a computing system set up to solve a second-order differential equation. You know, it's true. Okay, so this is about sound synthesizers, and then we go to, we get a bit more close to image. This is Dan Sandine, which is image processor, the first, well, not first, but like the open source modular video synthesizer, and he has this clip with sound.
It's a compact way of saying what it is to say that it is a general purpose analog computer, a general purpose patch programmable, meaning programmed by patch cables, analog computer, analog to distinguish it from what is normal.
Well, I'm going to skip here. I mean, it's obvious. When I have seen this clip for many years before I started doing this stuff, and you think, well, he's pedantic. You know, what is he talking about? Analog computer? Come on, you know, it's just a synthesizer. Until I realized, yeah, it's, you know, it's exactly what it is. I interviewed him to ask, you know, to find out like what he actually knew about analog computers. And then it turned out that basically for inventing the image processor, he had 3 sources of inspiration. Basically what he wanted to do is to build a Moog synthesizer for video. That was his first sort of, you know, rock star ambition. And then there was the thing that he knew about analog computers, so he basically used the analog computer to model his system. So this is one. So there's like all the modules are there. There's summers, there's multipliers. They're also called the same. I mean, you know, it's very obvious. And then the third influence are these modules, which are called nuclear instrument modules, because in the evenings to earn his money, he worked in a particle accelerator guarding the equipment. And they would have
concept
like
of how it works.
Sorry. So they would have whole walls of these modules, and basically what these do, like you have these particle accelerators, and then out come all this data, and then they do signal processing on it. But it was all analog. So these are all filters and comparators, and they sort of look at all these weird bips in the data, and then they sort of extract, and then there's counters, so they can count the number of particles they mean. I mean, I've been at CERN, like in Switzerland, and basically it's still the case that you have these accelerators, or if you have some kind of complicated looking instrument, and then the floor up, it's basically the rooms full of stuff, like, and there's still a lot of this analog electronic stuff in there. So those were the 3 influences for Dan. So this is one of the machines he built, which is now in the School of the Art Institute in Chicago. This is James Connolly, some of you might know him. Also a Video Circuits tribe member. And then this is Dan at the moment. I mean, he's retiring. He went on to develop the Cave system, like a virtual reality system for groups. And this is the Cave 2, which is basically the same, but not projected, but with like, I don't know, 120 HD screens. So it's like very high resolution. And he's using some kind of paint program. And then at the back, there's a storage room where he has his other IP, which he's thinking already about 20 years to perhaps restore. So it's, he's not into this stuff anymore. But I mean, he likes to talk about it, and he helps people, and he's very happy that James is teaching a class on this stuff at the School of the Art Institute in Chicago. Anyway, so this is him with his invention. Then there's the other famous one, the Rod-Etra scan processor, which I mean, it's very often used in a particular way, but it was designed also as a modular machine. So there's different modules, you can patch it in different ways. There has been also different versions. And then this is from Steve Rudd. The Rod-Etra synthesizer is a video analog computer. So, I mean, Rudd was an engineer, he definitely knew about this stuff. Yeah, so there's a different way to patch it. And then you get to sort of the hippie version of the interactive lighting experiment. Empiricism is the synthesizer Zen, like we sort of start with lightning empiricism and we end with the synthesizer Zen. Is that, you know, these knobs don't have any labels and you shouldn't, you know, relax. Just grab the knobs and go for it. And you're part of the system and you're part of the feedback loop. Which is interesting because there's a book about, like David Mundell has a great book about the history of fire control, which is exactly the same. Like the whole idea of cybernetics is about the first instance where people were thought as being elements in the system is in these fire control loops, where the humans were necessary to interpret the data and hit the button to do fire. So it's sort of interesting, it becomes this synthesizer Zen sort of floaty nice thing, but it's, you know, it's also comes from the same source. I mean, it's really the kind of weird echo of this military machine. Okay, my own stuff, I'm gonna just not talk. I started soldering, and then I stopped talking. And this is where I want to go. But I'm going to talk about my own work in Ljubljana. This festival continues, and I want to end with a clip of stuff I made. I'm working on a new film, and this is just a test, which is like vector graphics. So basically what I do, I use these analog computing units I built to not produce a video signal, but to control a beam which draws. And it's made with a machine which is called a stroke to raster converter. So it's not like a oscilloscope like here, but it's a kind of machine which they used in airplane simulator. So it comes from a English airplane simulating military facility. It's built for the military. And it's like 3 minutes without sound. Okay, thanks for your attention, patience.